Okay, this mini lecture is about equilibrium and components of forces. So first of all, equilibrium means that the net force acting on an object, which you can also write with the mathematical notation using sigma, is equal to 0 newtons. And so you'll see some examples of what I mean by net force here, but intuitively you just take each force that's acting on the object in question and you add them all up. And if the vector sum is 0, it's an equilibrium. So the interesting thing about that is by Newton number 2, since the acceleration is equal to the net force divided by mass, if the net force is 0, that's this condition, then that means that the acceleration is 0. And if the acceleration is 0, that in particular means that the x component has 0 meters per second, and the y component has 0 meters per second. So let's look at some examples of that, and this will also demonstrate how we can take components of forces. So first example, consider a weight sitting on a table. There are two forces acting on the weight. The downward weight, which you see with the downward arrow, W is equal to minus mg, and then an upward normal force acting. And this actually, the physics of this is that the weight is pushing down the molecules of the table, which you can visualize as little springs, and it's distorting the spring downward and these spring forces downward, and the result is there's an upward force on the table, and then the equilibrium condition can be stated as n plus w is equal to n minus mg, which is equal to 0. So in other words, these two are equal and opposite. To take a more complicated example, consider a weight, here it is over here, hanging from two equal length strings, and so you have two equal length strings here. The weight has a downward direction, as seen here, and these, since the strings are equal in length by symmetry, the tension in the left string T sub L and in the right string T sub R are equal in magnitude, but of course they're acting in mirror image angles of each other. And so you can take each one of these forces, T sub L for example, you can break T sub L into a y component, you can see my coordinate system over here, plus y, and a negative x component. And T sub R, you can break that into a plus y and a positive x component. And so if you look now at the sum of the forces in the x direction, that would mean that the sum of these two components has to be 0. In other words, this one is going to cancel that. And then the y component being equal to 0 means that the y component of T sub L and the y component of T sub R plus the weight has to be equal to 0 so that they all cancel out. So in other words, this vector plus this vector will be, when summed, equal and opposite to that vector. To take a third example, consider a weight on a ramp with friction. And so here's the ramp, angled with respect to the horizontal, an angle theta. And here's the weight on the ramp. And now in this case, it's more convenient to have a coordinate system x and y where the x is parallel to the ramp and the y is perpendicular to the ramp. And so we'll take components of vectors in the y and in the x direction. And so the result of doing that is we have a downward weight, as you see. Since the object is pressing on the table and the table is pushing back on it, we have a normal force that's perpendicular to the table. And then lastly, we have this frictional force which is acting up the plane, which if there were no friction, this object would be accelerating down the plane. So the friction is preventing it from doing that. So N is already in the y direction, and F sub F, the frictional force, is in the x direction. So what remains to be done is to take the W and break it into a component W cosine theta that's perpendicular to the plane, and a component W sine theta, which is parallel to the plane and pointing down. So this is pointing in the negative x direction. This is pointing in the negative y direction. Um, by geometry, the angle of the ramp is the same as this angle right here. And so we can now write um, equilibrium equations for x and for y, and the statement for the x direction would be that the frictional force minus W sine theta is equal to 0. That's the sum of the x component forces is equal to 0. And similarly, n, the upward normal force minus W cosine theta, the downward perpendicular to the plane force has to be equal to 0. And so these are the equations that would be used for equilibrium condition.